Good day and welcome to the Fluid Mechanics assignment. The question in question is found in the Mechanics of Fluids 4th edition textbook. In Chapter 4, Integral Forms with Fundamental Laws, it is a very straightforward question which makes it much easier to replicate and formulate an experiment. Choosing this question had a lot to do with its simplicity in how to replicate. All that is necessary is a 5-liter plastic water bottle, some press stick, and a sharp pair of scissors. After carefully cutting the bottle to match the tank in the question and adding some press stick to act as a stopper, the experiment may begin.
The apparatus shown in the report were used during the experiment, and the water was used as the liquid fluid in the tank. The plug at the bottom of the tank was then removed and allowed water to flow through the hole. The time it took water to empty the tank was recorded, and also the experiment was repeated 5 times. During each repetition, the height of the water level was measured and recorded.
In this section, we use FlowNext SC to simulate the unsteady drainage of water from a cylindrical tank through an orifice at the bottom. The model was built using 3 main components: a reservoir representing the tank, a restriction representing the orifice, and a pressure boundary representing the atmospheric outlet. The tank was assigned a diameter of 14 centimeters, an initial water height of 21 centimeters, and an outlet orifice of 2 centimeters in diameter. The transient solver was configured to capture the change in water level over time, allowing us to observe how the flow rate and velocity varied as the head decreased. 2 simulations were performed, one assuming a smooth surface and another including pipe friction to account for roughness and viscous losses. The results showed that the theoretical and frictionless FlowNext cases produced shorter drain times of around 21 to 23.6 seconds, consistent with ideal flow assumptions. When friction was introduced, the emptying time increased to about 29 seconds, closely matching the experimental result of 28.7 seconds. This confirms that including frictional effects in the model provides a more accurate representation of real fluid behavior, emphasizing the importance of accounting for energy losses in engineering simulations.
The key finding in this experiment is that in order to make accurate predictions, we need to consider the loss of energy due to the effects of pipe friction. When looking at the experimental collected data compared to the simulation with frictional energy loss, there is a 0.68% error. This is less than significant, and it just goes to show the level of accuracy of a simulation model that is used correctly for testing. In contrast, however, the correct theoretical calculations for this type of question require certain ideal condition assumptions to be made. When comparing the theoretical values to the experimental, we saw a whopping 28% error. This is highly significant, which also just goes to show that not all situations are ideal, and using ideal assumptions may throw off our validity of calculations by a very, very big margin. Having done this experiment, there is now a much clearer understanding of the difference between theoretical system responses and real-life responses. The experiment demonstrates that viscosity is a critical factor that cannot be neglected in a practical fluid system design. The viscosity reduces the flow velocity, thereby increasing the time required to empty the tank. All in all, this study effectively bridges theory and practice, emphasizing that for accurate modeling and optimization of engineering fluid systems, accounting for frictional losses is crucial.